All right, pause, switch your paper with somebody else right now. Let's go.
You done?
I don't care if you're done or not. Switch with somebody else. All right, so which type of, so correct it for them. So like just scratch through if it's wrong and then add a little addendum or addendum to it. Switch with somebody
Teachers, please excuse all juniors with last names A through L to the cafeteria at this time. All juniors with last names begin A through L to the cafeteria at this time.
Yeah, you guys are good. I can't be that person.
Okay.
Bye.
Well,
I think you can bring your stuff. So yeah, I think so. Watch the video from today. And who's leaving? 1, 2, 3, 4. There are 4 of us.
Sean, just send that paper tomorrow, please. Actually, I'll send it.
Yeah, there's 4.
Actually,
Okay.
grade it. I want to see it
Okay.
again. But
Peace out, means get out of here. Bye. All right. Which type of compound will evaporate the most quickly? Courtney, tell me what you think.
I said non-polar.
Good. Nonpolar covalence because they will. Oh, so I'm just going to say nonpolar molecules because that is indicative of a covalent compound when you say that. So those of you at the back, you have lots of room to scooch up now. Okay. So correct that for them because we're talking about London dispersion forces, so they'll evaporate very quickly. The stronger the IMF, the what the volatility, AJ.
The stronger, the less volatility.
So what does volatility mean?
How easy it will turn to gas.
Okay, so how easy it will evaporate? Okay, cool. So lower the volatility because it's going to be really strongly held together. Emma, the blank, the vapor pressure. Emma, we'll start calling you Emma. Okay. Because right, so if it doesn't turn to gas, it's not going to make vapor. Doesn't make vapor pressure. Good. And then Arushi, viscosity. More viscous because it's not going to be as freely flowing because those things are kind of closely packed together or closely, tightly held together. Okay, so who's gotten 100 so far on warm-up? Okay, don't admit it, I guess, if you didn't. Which of these actually accurately portrays basically evaporation, so liquid becoming gas? Anybody? 1, 2, or 3? I see a lot of 3s. Okay, why not 2? So if anything, there's still some molecules that are tightly kind of close together. It's probably going to look like a water droplet, like a liquid water droplet if there are that many that are closely knit together. It could be 2, but it's most likely 3, because many times when our solid goes to liquid, yeah, there's still some attractions there. But when you go to gas, they're dispersed very widely, and so that's likely not going to have any attractions between them. Okay, and this is water, so what is this little dash line supposed to be indicating? Hydrogen bonding. Why is this not right? Right, so this is what Levi was asking yesterday, and I really wanted to do a good job of depicting that for you guys. This is a chemical change because we're actually changing the chemical arrangement of the atoms. That is not going to happen in a physical change or physical evaporation process. This is only going to happen in a chemical reaction. These 2 things are physical changes because there's no chemical rearrangement of their actual atoms within the molecule. That's why we consider those physical. They physically just change appearance, meaning gas or liquid. All right, 100 all the way? Less than 100? The rest of us, okay. But I don't want to know what the less was. So give that paper back to that person, because I'm going to look at that. I want to see where Ms. Hudson's work. We are going to do a couple heat curves and cool curves, and then phase diagrams. Write out the examples with me, because you'll see some diagrams that are very kind of familiar to you. So I don't think I need to hit everything as hard as you probably think I do, because you guys have a decent memory from honors chem. So this actually is not, this doesn't relate to our phase diagrams at all. Questions? What's up, Bobby? You guys good? Okay, I just make sure you guys are good. All right, so this doesn't relate to our heat stuff really all that much. But what curve is this called? Maxwell-Boltzmann curve. That's just the name of it. And it's supposed to give you information about what? Shout it out. Okay, so this is V, this is speed, meters per second or miles per hour. Think about like in your car. So this is speed of molecules, which speed we relate to kinetic energy, basically how fast is it moving, and it relates it to, in this case, these are temperatures. I know it's not labeled, but those are temperatures in Kelvin. And what is this? Right, so the number of particles traveling at these given speeds across the ranges here. So this is number of particles. And if you actually wanted to figure out the number of particles, you could do the area under the curve, right, calculus? Did you just figure that out? Yeah, you could. Calculus, yeah. All right, so relate this information to vapor pressure. Talking to groups, you have 30 seconds. Relate this to vapor pressure. Remember, these are gases. Sorry, these are all gases. Because gases are what we talk about traveling at a certain speed. All right, pause, 5, 4, 3, 2, 1. Arushi, explain what you think relates, how this relates to vapor pressure.
Well, if you increase the temperature, that will increase the average kinetic energy, and then that will increase the
Okay, increase the, give me 2 factors about frequency. Give me 2 factors about collision with the wall.
like effective collisions.
Okay, give me the factors for that.
Frequency and like strength, I guess. Like
Frequency, which is the number of collisions, and,
how strong it is. How
okay, so force of collision. Number of collisions, force of collision. Okay, so increasing temperature increases average kinetic energy, so the speed that they're traveling increases the frequency and force of collision, which,
that increases vapor pressure.
because what the heck is vapor pressure?
It's the amount of collisions.
With the container wall, right? So we're talking about vapor pressure, which is the number of collisions in the container wall. If you have more frequent collisions and more highly forceful collisions, you're going to increase the vapor pressure due to the container wall collisions, basically. So I just wanted to walk down like the domino effect of how does that work and how does it relate back to kinetic energy and so forth. So the particles that are the blue ones, they're at 600 Kelvin. You see that up here? So their range is very wide. So top speed of 1,500 meters per second, but most of them exist at what speed? Yeah, about 700 there, right? So the average speed, which is the bell curve average, is higher than the cold ones at 20 and at negative 100. Relatively, what are the average speeds of the negative 100 Kelvin particles? 300, and the 20 Kelvin, about 400. So despite the fact this is average, right? Does every particle meet the average? No, because like I can say, okay guys, the test average is 70. We got extremes, you got lower and higher. Same thing here. Some particles are moved faster, some particles move slower. So now this is inside of a closed container for vapor pressure. What happens if I open the container? What happens to the particles? They release, so the vapor pressure lowers because the particles are escaping. What do you call it when a particle escapes through a small hole? Effusion, right? And eventually, if it goes from a highly concentrated area, like if I brought in Krispy Kreme donuts, all those small particles, right, hit me in the face. But eventually, what happens to the small particles? They diffuse across the room, and then you start to smell them. But they're traveling fast enough to get to your nose in probably a minute or so. Because foods, I smell them daily. It smells delicious. But it's traveling this far because it's diffusing from high concentrations to low concentrations. So a little bit of bio review, right? A little bio, okay. All right, so that's basically what the vapor pressure section was on. And this is a fact about if you have vapor actually forming, so like going from liquid state to gaseous state or to vapor state. So you have to have enough kinetic energy. So here's our liquid. Not all the liquid's going to evaporate most of the time. There's some that move slower than others because that's temperatures and average. There's the range that still exists. So only the fastest ones will be able to pop out and form gas, and pop out and form gas. But if this is a closed container, it's a really good container. Okay, so if it's a closed container, what actually could happen to that gas again? It could condense, right? And so there is eventually going to be a constant amount of gas, even though it's changing. It's dynamic equilibrium. This is a physical equilibrium from liquid to gas. So we're going to get a constant vapor pressure at some point if we're at a constant temperature. But as soon as I pop the top of that off, I'll start to get more and more of them that turn gas. Why? It was a closed system. It met equilibrium, went back and forth, evaporation, condensation, evaporation, condensation. As soon as I popped the lid, more turned to gas. Well, maybe, give me equilibrium. Okay, so my stress was increase the volume, so there's less pressures, so the gas particles escape. Which way does it shift? Yeah, it's going to be Le Chatelier to shift more gas, and more gas is going to form until it gets back to reestablishing equilibrium. I'd have to put the top back on there to actually reestablish. So eventually, like, we can start relating physical equilibrium to, like, our examples we're doing here. All right, so only a fraction of them will escape because of the whole kinetic energy component, but they can go back to liquid state as well. Okay, great pictures, guys. Good job. All right, so a couple more things. This is going to be a heat curve. I'm going to sit here for a minute. Sketch yourself a big heat curve so we can actually annotate on it as we go. So you're not taking extra notes on top of this. This will be actually like overlaid. Sketch yourself a heat curve. Not recommended, required. Mrs. Johnson? So basically today's all about phase change and why do things phase change and how does the intermolecular forces kind of come into play with this. And you guys probably know a lot of times we use water as our main example because everybody knows when water melts, the temperature and everybody knows when water boils, so we use it for a common background knowledge we have. Okie dokie, that's good. Alright, so what did I call this earlier? Heat curve. Is it a curve? No. I hate that we call it a heat curve because it's actually a heat stair step, but we can't call it that. Just like we call hydrogen bonds a bond, it's not really a bond. So label this heat curve. What are the plots against? Temperature and time. So it's like as you heat something over time, what happens to it? Does it phase change or does it not? And then you'll notice that for just heat, just thermochemistry, not thermodynamics, but thermochemistry, what is my unit of temperature? Celsius. Remember, like, Q is equal to MCAT, MC delta T, that delta T is in what? Celsius. But when you go to thermodynamics, delta G minus, or delta G equals delta H minus T delta S, it's what? It's what? Kelvin. Okay. Well, you know, step one. Yes, ma'am. Thank you. Bye. I did it the whole time. So, step one, was it flat or was it diagonal? Diagonal, okay? So as our energy flows, let me go back to my actual thing here. Let's just talk what we know first, then we'll write down the details. Okay, so down here, we're at ice, right? We're at solid ice. When is it no longer solid? Okay, it starts at 0, so it's all solid here, right? So as I add temperature, the temperature is going up, up, up. But what's happening to the ice? I'm just going to make ice as like little atoms like this, little balls. They're actually molecules, okay? What happens to this as I heat? Okay, so the molecules begin to, first of all, are these moving quickly? No, this has low kinetic energy. Okay, so as they start to heat up, they start to vibrate a little bit more. They start to try to separate some, but we're not going to separate so much we melt. We're just going to start to get some motion to us, okay? So motion begins, increasing in kinetic energy. And more than anything, motion, which gives us the kinetic energy aspect, what's holding the ice together? Hydrogen bonds, right? So there's some hydrogen bonds here, right? So those hydrogen bonds have to kind of loosen up a little bit as we allow for this to eventually turn to liquid. So the energy that's being put into that solid, the energy is used to overcome hydrogen bonds. That's really a lot of what's happening there in that diagonal stage. All right, so as we then get from 0 to here, we see that you're not changing in temperature, but you're still melting. Well, how is that happening? There's still energy being put in. Does energy always correlate to delta or to temperature changes? No. Okay, so energy, that's what I was trying to lead you to here, okay? So if I change temperature, the definition of temperature is average kinetic energy. Okay? So is there temperature changing here? Yes. So average kinetic energy of the particles increasing, and that's what we're saying here. Kinetic energy, motion, we're increasing kinetic energy. And there's a little bit more energy kind of coming into play. Now, there's another form of energy that talks about like positional energy or relationships between bonds. Potential energy, okay? Potential energy is not going to correlate with temperature. So across from the plateau here where I'm phase changing, number 2 is a phase change. Phase changes will not have temperature changes ever. That's because it's potential energy that's changing, not kinetic energy that's changing. The positional arrangements began to kind of get in flux, meaning the solid here starts to kind of get a little loose. So that's us overcoming the hydrogen bonds, which is potential energy changes, not kinetic energy changes. Okay, so it's still ice, and it's still kind of liquidy, icy liquid. And then we get here, and now at this final point over here, are we liquid or are we solid? Right there. We are fully melted, right? So here, we're like solid, just barely starting to turn liquid. We start to turn liquid, liquid, still some solid in there, liquid all the way. Okay? Now what happens? Temperature change again. So during that temperature change, what actually has happened to the particles? They're starting to really move faster, right? So the particles are getting kind of flowy. Particles are all moving places. So they're moving faster, so basically you're saying increasing what? Increase in kinetic energy, because remember kinetic energy is going to be reflected in a temperature change. When you have a temperature change, it's because your kinetic energy changes. That's just the definition of what temperature means. Okay? We're still probably overcoming some intermolecular forces, right? We're starting to get moving faster and faster and faster, so there's a little bit of potential energy change as well. And we get faster, all the way up to here. We're moving super fast at this point. A lot of kinetic energy change, 100 degrees to be specific. So now I'm liquid still here, fast moving liquid particles. What happens here? What happens here? Okay, so we start to phase change from liquid to gas. Okay, so the liquid particles, this is what our warm-up was. Liquid particles that are kind of attracted to each other start to do what? Don't say the word break. Overcome their attractions. I'm trying to coach you guys in your explanation, so don't say break. Break means break bonds likely. Overcome attractions is our fancy way of IMFs, right? So you're going to take our liquid, which are kind of closer together, and overcome their attractions and let the gases become free. So we're overcoming attractions. And is that a potential energy or kinetic energy change? Potential energy change. Because, I mean, attractions aren't just going to overcome themselves, right? You got to give them a little oomph. You got to give them a little energy to make it happen. So the energy, though, doesn't transform into temperature change. The energy changes into potential energy, which is overcoming IMFs. So there's a lot of connections here. Last stage, what's happening? The temperature is changing, so what's happening to the particles? They're moving faster. So these gases are increasing in their kinetic energy and starting to move very, very fast. So the fastest moving particles are the hottest, right? So they're up here at like 140 degrees. Who's ever like opened a pot of water and the steam comes out and it's like super duper hot? Okay, warm water, Warm water's like down here at 80, pretty manageable. You can put your hand in that, probably be fine, close to it. But a lot of times steam, a lot of steam comes at you at once. It's going to be really, it could burn you. So that's because it's moving very quickly because it's very hot. So that's our temperature change with that. Now, you're still probably overcoming a couple IMFs here and there, but most of them are overcome on the phase changes, whereas the motion increase is happening on the diagonals here. Okay? Plateau means what? Phase change, and we're overcoming what? IMFs. Are we increasing in temperature? No. Those are the three main points, yeah.
There's like an absolute zero, but you can get as high as
Yeah, there's no absolute high temperature. There is an absolute zero. Not that I know of, though. I don't know. All right, so phase diagram. So that's our heat curve. Let's do phase diagrams real fast. And then I think I told you everything here. This is probably more wordy than you really wanted. Oh, I didn't get to tell you heat of fusion. That's what I forgot to tell you when we were going through the diagram. Write down, where would you put heat of fusion, the energy it takes to fuse? What's fuse mean? To melt. Where would that go in your heat curve? Okay, which flat part? First one. Okay, so this is our solid, liquid, gas, heat of fusion. Okay, that's our kinetic, or that's kilojoules per mole, which is the amount of energy it takes to overcome the attractions from solid to liquid. So this is the potential energy it takes to overcome IMFs for that solid to liquid phase. And we can calculate it. This is, I think Alvin said this yesterday, delta H is equal to Q over mole. You can always rearrange that to do Q is equal to moles times delta H. So some thermochem review for you. Moving on here. So this is kind of like all the information I'm videoing right now if you want more of this. But this is our 1, 2, 3. So this is our temperature changing, so the liquid phase of our number 3 here. So we're going to increase until we meet the boiling point. All the liquid's going to be in vapor form after soon, and then the temperature is going to remain constant as we do our next phase change. So what is this one going to be called? Heat of vaporization. That's the temperature, or that's the energy per mole of water or molecules in this case to overcome what? IMFs between what two phases? Liquid and gas. So I'll go ahead and tell you, and this is approximate, don't kill me if it's wrong. Delta H of fusion for water is like 6.01 kilojoules per mole. 6.01 kilojoules per mole. And then delta H vaporization is like 40.6 kilojoules per mole. It's really close to that, okay? Huge difference. Why? Both of those are energy to overcome IMFs, right? But what's the big difference? Say again, AJ? But they're all hydrogen bonds. It's all water, right? Hydrogen bonds all the way. But what happens between solid and liquid? Are we overcoming all of the hydrogen bonds? No, they're still going to have to be attracted. How else are you going to get a droplet, right? They got to have a little bit of connection. So you're going to have solid going to, oh, look, big whoop. There's still a little bit of attraction here and there, but it's just a little bit of overcoming, maybe overcoming 20 or 30% of the hydrogen bonding. Not all of them, because there still needs to be some sort of attraction. But then you get the big boy down here, because you go from partial attraction to like, I don't even know I have a neighbor, okay? Don't even know I have no hydrogen bonding at all. So it overcomes the 70 or more percent of them, so that's why the energy is much, much greater. Cool? Making sense so far? Some of it's common sense because you guys are smart cookies. Okay, so, and then this is the end here. So at this point, we kind of hit the top. We got to the gas phase. We're done. And just remember, this is all phase changes. Nothing chemically has occurred. So everything that was chemically bound in the first place is still chemically bound. We haven't broken a single bond, unless you say hydrogen bond. But we all know it's not a bond. Cool? Give me a thumbs up when you're good to go. All right, so those are my main points for heat curves. Cool curves, what do they look like? Opposite. So start. What's this first one? gas, and then go to condensation, and then liquid, and then freezing, and then solid. Okay, so while the blue one in this case took energy, like endothermic, took energy to go all the way up there, this pink one would be exothermic, to release energy as it like kind of brought down to a more stable form of gas, or solid. These are some pictures for you, okay? Draw your phase diagram. This should be our last thing for today. Phase diagram. Yeah. No, because the constant amount of energy, it won't. It'll require a lot more of that energy, meaning a longer time to get a vaporization. So you'll see on this one I drew everything equally, but if I were doing it for time, it would probably be like melt, liquid, evaporate, gas. It would actually be different there. Alvin, did you draw your phase diagram? Kind of, or yes? Thank you. All right, so this is our easy phase diagram. How many times have you guys seen phase diagrams? Just normal chemistry? You guys do things in middle school? Okay, this is considered prior knowledge in AP, like I'm not even really supposed to teach this. But good lord, some of you guys have been in chemistry for 2 years, 3 years. So, you know, of course with this year included. So it's been a while, so I need to make sure you understand how to read it, how to draw it for yourself. So most of the time it's something like that, solid, liquid, gas. Between the lines, we can think about them as phase changes. So you guys are done?
Yeah.
Super awesome. Yeah, okay. I didn't think you guys would be back. All right, jump back in with us, okay? So listen up, crew. You're in charge of teaching them the other stuff. Cool, good. Glad we agreed on that. So solid, any point in time between the solid and liquid, what's that phase change called? Melting. Any time between solid and gas, what's that phase change called? Sublimation. Any time between liquid and gas, what's the phase change called? Vaporization. Backwards, liquid to solid. Freezing, gas to liquid. Condensing, and then gas to solid. Deposition. Thank you. So those are, we can connect it at any point in time between the places of the graph. But I might say, what is the melting point at 1 atmosphere? So then you must consider how these axes are different than our heat curves. This is pressure on the y-axis and temperature, again in Celsius, on the x-axis. So pressure versus temperature, no time involved. You have to look for where we are. So we live at generally 1 atmosphere, like normal atmospheric pressure. So you are here at 1. So then if you're looking at that, I'm sorry, this graph is kind of small, scooch up if you need to. So solid to liquid, we're going to look and see where that crosses at the 1 atmosphere mark. So 1 crosses between solid and liquid right there. And if I drop down, that reads to be, 0 degrees Celsius. Who would have thunk? This is water, right? Water melts at 1 atmosphere at 0 degrees Celsius. But if I were looking at, let's look up here, I have no idea. Where would there be 218 atmospheres? Where in the world? Bottom of the ocean, right. So bottom of the ocean, what is the temperature that water melts? Bottom of the ocean, you're looking here. Dash over to where the solid and liquid interface here, and then drop down. Guesstimate. -10, I don't know, -10 degrees Celsius is where it would melt. So the melting point, freezing point, all the phase change points will be different depending on what your pressure is. That's the main point of seeing a graph like this. So then what's the boiling point at 1 atmosphere of this substance? 100. So if I scooch over from the 1 atmosphere, scooch, between the liquid and gas phase, drop down where they interface together, that happens to be 100 degrees Celsius because this is water. But I can give you unknown substances, of course, these are familiar to you. So I could also ask you, what's the sublimation point at 1 atmosphere? There isn't one. It doesn't sublime at 1 atmosphere. Water could sublime on the top of Mount Everest. So Mount Everest, higher or lower in atmospheric pressure than where we are today? Lower, because we're on top of a mountain, less air pressure on top of us, lower atmospheric pressure. So let's call that just 0.005 for now. So this point here, scooch, 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 between the solid to gas, and it would sublime at, I don't know, negative 20 degrees Celsius or something like that. Okay, so you can definitely get a lot of information from a graph like this. You should know that in the middle where the solid, liquid, and gas interface all together, that's our trickle point. There's one temperature and pressure that will occur at. And then this point up here, eventually, once you get to such high pressure and such hot temperatures, think about it. You have a box of air, right? Squeeze a lot of pressure on it. Ooh, okay. And then you're trying to heat it up. What are the particles trying to do? Speed up and expand, speed up and expand, but you're pushing back and speeding up and expanding, going back and forth. Can it become a gas? No, you're pressing it, you're compressing it together. Can it really become a liquid or stay a liquid though? Not really, because you're pressing it, but it's also trying to expand at the same time. So we call it the supercritical fluid. It's after the critical point up here, and so it's an indistinguishable phase. It's not a liquid, but it's not a gas, so I kind of call it liquid. Okay, it's kind of like a liquid, but it's neither. So that's why it stops and it doesn't continue to line up. So this point up here is where you get the liquid. I put a C in there now. Okay, so that's like the indistinguishable phase. Okay, that's because of the differences in pressure and temperature. Okay, CO2, just one more example for you. Where's the sublimation point at 1 atmosphere? Negative 78 Celsius, right? Like we don't experience negative 78 Celsius. So at us, at 1 atmosphere, we will never ever see solid CO2 go to liquid. We'll only ever see it go from solid to gas, unless we put it under a lot of pressure. Okay, so if I did put it under a lot of pressure, let's say 15 atmospheres, what would I see? I would see what phase change? So I would see melting, and then I would see, if I heat it up even more, I could see evaporation. But I'd have to have some really cool steel drums to get that to pressurize like that. All right, so a lot of review. Do you feel okay? I think I have like 2 more things to tell you, like random facts. Skip that. Drill more. Oh, yeah, let me show you this. Okay, so critical point of CO2. Will you hit the lights for me? All right, so this is CO2. This is 27 degrees Celsius, so it's liquid. Right now it's liquid because it's under a lot of pressure. So it says the temperature rises as the liquid CO2 evaporates and the fluid level rises up the inside. So this line shows the start of the liquid. So it's gotten more liquid, more liquid, more liquid. It's continuing to rise in temperature. You know, this is really, really exciting. So we're gonna speed that up. All right, and that's where, I can click it soon enough. That's where, let me go back. So 33. Okay, that's where it actually went to the indistinguishable liquid state. 33 Celsius. It's under a lot of pressure, under a lot of a high temperature. Let me go back to that graph. I just skipped it. Where does the critical point occur? So above what temperature? 31, so we hit 32. And so it must have been on a really high temperature because that's where you had your indistinguishable liquid. Okay, so they actually showed it to you under this weird device. Okay, and then this is just fun facts. Supercritical fluids, which is what you can get. They're used in the real world. A lot of times we're extracting caffeine from coffee beans, which I thought was kind of cool because I'm a coffee person. What? Okay, and then this right here, you should know what's in that. What's in it? Say again. Carbon dioxide. What state of matter? Liquid carbon dioxide. This thing is so pressurized, that's why you can't get it hot. I know it's just for fire. I think that's kind of weird. You're not supposed to get hot. But when you open it up, what happens? It releases pressure, so when it releases pressure, what comes out? The liquid, okay, so you're pressurized, it's liquid. You release the pressure off the top of it, the liquid immediately turns to gas and does what to the fire? Say again? So I like the, kind of like the word suffocate, there's another word we should use. So, there's all this oxygen and nitrogen and other stuff in this, right? The oxygen's fueling the fire. So CO2, which weighs 44 grams per mole, oxygen, which weighs 32 diatomic oxygen, okay? So who wins? The CO2 smothers, yeah, it's like a CO2 blanket, smothers the fire, pushes the oxygen out of the way, so there's no more oxygen to fuel the fire, and it says, no fire, not in my house, and then it gets out, okay? So it's going to smother the fire because it's higher molar mass, because of its gaseous state. Okay, smothers the fire, dense vapor. And there's us. Where are we at? We're not up there, okay? Where are we? Where's our water boil? Sea level. I'm hoping to be down here like this summer, going to someplace, but maybe up there, I don't know. We're going to do a road trip to California, I think. We're still working on it,
It's
yeah.
like 3 days.
I know! We're going to see all the national parks.
That's really cool, but it's also
I know. I told my husband he's going to take off like 2 weeks. He said, I'm not a teacher. I don't have the summer off. He's like, I know. Okay. Oh, and then I've been there. There you go.
Big Mountain King.
Yeah.
Oh,
And
you're
then
from- you're
water
from-
boils at 79. Thought that was kind of cool.
That's really cool.
Okay, so we're going to do our lab now.
Yeah, you know, like climb mountain 12.
Okay.
You should do that. Bring a hot plate.
I'll play and try all our data. Okay, so
Dang it, Sean.
here you guys go. Oh, I think I left them in the back. Are they in the back? Yeah. Alright, so you guys have a lab. It's not in your packet. You guys first. This is like a 30, 45 minute lab maximum. You'll see on the board it says pre-lab, ethanol, propanol, blah, blah, blah. So, is that okay with them, Riley? Get started. I'm giving you guys 10 minutes or less to draw your structural formulas and then wait if I can or not. Okay? Thanks, Riley. Yes, you might have to get up. What's up?
You guys knocked out all of the yes or no's and how much.
Okay. Draw, and then we will do the lab. While you guys are doing your pre-lab, I'm going to take attendance and show the announcements. Because we have a celebrity in the house. Or two. What, Sean, what are you running for? Sean, what are you running for? Okay, he's running for VP next week. Next week. Jack's running for student body president. Who else is running for something? Or just running? Nobody's just running? Alright, thanks Alvin for passing this out.